Welcome to Renaissance Charge Videos. I'm Rick Friedrich. Today we're going to talk about the high voltage spike on the circuit of the 4 DualPole mini motor, and the same things will apply to the larger model, which I decided to do in a separate video. So today we're going to look at this capacitor across the MOSFET. And it's very critical in many ways, well, in several ways. So we're going to go through the basics here because not everybody has the opportunity to look at all the previous videos, and there are very many of them now. So let's go over the basics. First of all, we're going to look at what this motor is. So again, we have to start with what I've talked about before, the selfish circuits, loving paths idea. So typically, a regular motor is a DC motor would have a source, such as a battery or a DC input, if you're looking at a DC motor, which is a closed loop across the inductors or coils that are powering the motor. So it's a closed loop here, and you could either run it with constant current, or you can pulse it and provide a frequency-based regulation, which is what we're doing here. So in other words, you turn off the motor more, there's going to be less power in the motor on the basic level. So now when you pulse it, or even when you turn it on initially, there's a thing called reactance, and it's a resistance to the change of flow, so to speak. Because of the coil, there's a reaction that's going to take place instantly to that, which creates a voltage spike. And there's many theories or ways of understanding it that are overly simplistic and miss a great opportunity, which we're not missing with this motor. So normally this is a destructive force here across the coil and the contacts of the switching. So if you just apply even a DC, no pulsing, you're still putting a pulse on when you're connecting the battery up to a closed loop. Just like when you flip the switch on a light bulb, on a light switch, you'll see that there's a sparking that takes place. So at that moment, or if we repeat it with a frequency, there's going to be this negative energy flow. And that's the terms that are used, negative. And we're going to look at Wikipedia saying the imaginary element, the useless element, the destructive force, so forth. So this is a diode will be going in the reverse direction, one across the MOSFET and one across the coil. It's the snubber system, or the flyback diode, and there's a variety of ways of describing that. So it's a suppression system that prevents blowout. So we're sending that back into the reverse, back into the coil, and hopefully that diminishes the spike. We're going to look at that spike today and manipulate it to our advantage. So what we do, instead of closing that loop there, we open the loop to a charging battery. Alright, this is the basic setup. This is the first stage 1, as we've called it. Now we're charging a battery. So normally you have this diode cross here maybe with a capacitor, resistor, to try and suppress this negative pulse. It's considered equal backwards as it is forwards. However, that's not true at all. That's only in relation to the parts that you're using. So for example, when we've gated it out here, and remember these batteries are in series with each other, they're not in parallel. So this is not an amplifier circuit. The batteries here are in series with each other for 24 volts. So there's 24 volts across there. So what's happening is, as I increase the size of this battery, I know some of you are going to say, well, I've heard this before, Rick, but you have to follow what I'm saying in this video to get to the point that I'm going to make with this capacitor across the MOSFET, because it's critical to your efficiency, and this point is a critical point. As the battery increases, so does the amount of charge taking place over time with the same amount of input from this battery. I don't believe that actually the energy is coming from this battery ever. Even in this scenario, the energy is not coming from the battery. And that's, if you study enough, high up enough in physics, you'll realize that the energy is coming from the ether, or what they're going to talk about, dark energy or whatever quantum nonsense that people believe today. The point is, this energy is not powering. It is indirectly, but as a trigger. As this loop closes, the battery discharges itself, okay, and the load runs. The battery discharges itself at the rate of the load, and that might sound silly to say. Oh, you're just saying the same thing, Rick. It's still discharging. But the point is, the energy is actually coming in from the environment to power this load here. It's just that we're wasting the energy that's in this battery. We're dissipating it at the rate that the energy is flowing in here. That's very, very important to understand the difference. If you think that the energy is in little packets of balls of energy in this battery, and they're somehow coming through here and powering this load, then you're going to be very limited in what you can do. You'll never get over here. This will not make any sense at all. You'll never, in your mind, be able to conceive how this battery is charging at the rate that this is discharging, while this is also running the motor normally. Now, we've shown that for years in the fan kit and all these kits, where we take a brushless fan like in the back of your computer, or the fan that's in this oscilloscope, and we literally change the direction of these diodes, and now we place another battery. We run the fan still at the same CFMs, same airflow, same RPM, with the same amount of energy coming from this battery, and yet now we're charging this battery. And if we add the regular circuit to it, we can even charge this at the rate that this is discharging. Now, are there losses? Yeah, like I said, every time you run these things, you have losses in your system. So if this battery is charging at the rate that this is discharging, then we have to have more than 100% of, because we have losses. Every time you charge and discharge a battery, it's never 100% efficient. It's quite a bit less. So if we even charge this where we can swap these batteries around, then we've had to do maybe 150%. Not to mention, so we've got like 2.5 times the energy from one in to 2.5 out. Because we've had to power the motor, that's one, charge the battery, that's 2, and compensate for our losses, another half maybe. So the fact that this charges at all, when nobody does this, generally, shows that it's one of the biggest, I hate to use the word conspiracy, misconceptions in electronics at the most basic level. When you think about the negative component, the reactance, when you get into reactance studies, which we're going to talk about in a minute, the fact that the negative flow in a pulsing system is equally understood to exist. It comprises half of the study of energy itself. I don't know how to describe what I'm trying to say exactly, but in simple terms, but it seems that most electrical theory and study is based upon purely the positive elements and constant current. And that's so widely understood and it's pretty basic. But the other half of the story is the changing magnetic and capacitance fields, flows. And also, the whole idea of the pulse is very common, and there's so many things pertaining to the pulse, but in the way of suppressing it, in the way of protecting your electronics. So this is really important to understand. This basic circuit is so simple, and yet is, again, so neglected. I've done this video now a couple of years ago. What is it now, 3 years? And I've been showing this stuff, for about 14 years now, and many others have before. But the point is, this basic circuit is the key. If you don't get the basic circuit, nothing else is going to flow. You're going to be still thinking in these terms here. And that's what I find. Engineers all over the place, doesn't matter how high up they are, unless they specialize and understand this, they are still limited and mystified and confused with all their degrees and everything, and stuck in this little box here, this little limited worldview that we have from way back, going back to Edison days and Morgan and so forth, and just even before that, in Maxwell's day even, because people didn't understand how this could be utilized. It was a destructive force that needed to be prevented. So we need to get beyond that. And here's the basic diagram again with the bulb, closed loop, constant current. So, but even then, in order to turn the switch on, unless you had a resistor slowly turns it on, soft switching, then you wouldn't have this. Even then, even with the highest resistor value, you're still going to get a pulse, always, when you turn some kind of switch on. So there's always this element taking place. Whether we ignore it or suppress it, it's there. So now we're going to get specific into this in two different ways. One is the third stage process, which we'll talk about later. But first we're going to talk about the next part. So we can look at it like this. So normally we have the switch on the negative side. Doesn't really matter, but these diagrams I made up a couple of years ago just happen to have it on this side so that it was easy to view, I guess. So anyway, what we found was, like I said, as the battery is bigger here, it received more charge. So the energy is coming in from the environment. It becomes a negative resistor. This is a negative resistance here, and the energy is flowing into the battery because it's not coming from this battery. This battery is discharging itself. Still closing the loop, right? And there's two events that are taking place here. Once when the switch closes, you have this inductor changing, right, until it stops changing and current flows. And that's where Kirchhoffs Law applies, only after it stops changing. So once it becomes a constant current, where nothing's changing, it's just going in that supposed circle, then that effect stops. So at the moment of switch closure, boom, there's something that happens faster than the speed of light. And Rick, you say, Rick, come on, it's not possible, blah, blah, blah. But that's, if you study this out, you'll see what I mean. Something happens at the moment of switch closure that kind of opens up a door along this whole path. Boom. Suddenly, it's like you turned a key and it opened up this door and the room gets filled with gas. So it's like that, it's like a gas flowing in instantly. Suddenly, it's like turning these into solar panels or lifting the veil off the solar panel, and all these are solar collectors, and suddenly they're collecting energy from the sun. So it's like that. As soon as the switch closes, boom, these are exposed. So naturally, the bigger the surface area, the more charging takes place. And so you try smaller batteries, and I'm talking about good quality batteries. Don't start off with brand new batteries that haven't been sitting on the shelf to properly do experiments. You can worry about rejuvenation of other batteries later on. Start off by understanding these principles. So you're looking at this battery, you have a 2 amp hour battery here, and you get X amount of energy. Say you get factor of 2 in energy. Whatever you want, however you want to define it. And then you have 200 or 2000 amp hour battery or whatever. And now you have, say 200 times, or a factor of 200 instead of 2. All this is staying the same, relatively speaking. Hasn't changed much at all. But we just changed here. And suddenly we have this enormous gain from before. Why? Because this was a bigger receiver. So this doesn't at all relate to any kind of electron theory. It's nothing to do with electrons flowing. I don't personally have a theory of electrons. I would probably tend towards Tesla's view, which he did believe in a particular theory of bigger electrons, supposedly. Doesn't matter to me. I'm not dealing with constant current flows most of the time. I'm dealing with pulsing, almost everything that I do. All my chargers, everything is always in a state of change. You could call me electrically one of those guys who's given to change. We've all known those people that are given to change. And I'm not given to change personally, but in electronics I am. Anyway, I'm always given the change of improving my products as well. So what happens is, then the second thing is this coil is changing, right? And then we turn off the switch. We open up the switch, and this is what people mostly focus on, what they call the back EMF, when the collapsing of the coil takes place. Well, is it the current flow that's causing the back EMF? Yes and no, depending on your definition of terms. It's the moment of switch closure again. So we're flipping another switch. So when we open this up, this coil, so to speak, becomes a switch. Like you could look at it as a source, and that's the way the books talk about it, which we're going to look at a little bit. So they're thinking that, oh, the energy's stored in this, and it's coming out, and it's imaginary, can't do anything with it, blah, 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 which is obviously foolish to say, and yet almost everybody's saying that. Well, this is creating a switch. For those of you who are familiar with these motors, you know, obviously, that there's more to it than that. So what happens is, you can see we'll see the spike in a minute here, at the switch closure of the collapsing of the coil. I'm not doubting that there's a collapsing of the coil, but in this case, this is just like closing the switch. Opening the switch is doing the same thing. It's creating a new flip. So what happens is, that's when we see the big spike. But there's two events, and that's what we got to remember. The closing of the switch initially, because remember, it's related to the changing field, the changing circumstance. You're creating a great potential suddenly both ways. And so the energy rushes in to these parts, these receivers. So when you create a potential and there's a source of energy, it saturates them, it affects them. So that's the key to all these kinds of systems, is that we're creating, voltage, we're creating potentials, and we're getting the energy from the environment in. And remember, the environment is always, the creation is made in such a way by God that it always seeks equilibrium. It always seeks to balance everything out physically. So what happens is, we have all sorts of changing environments in which, if we understand how they work, we can tap into them, right? So we do that in any kind of energy system, more or less efficiently or inefficiently. So that's the basic. You got to understand that there's two events, because if you just focus on the one and miss the other, then you're going to do bad engineering. And it's going to blow up your parts, for one thing. And that's what we're trying to avoid here. The focus of this video is on this capacitor. So normally, if we go back to here, and we have a diode and a capacitor here, a snubber system, usually with maybe a resistor as well, because we want to not allow any pulsing across here, and we don't want this big voltage to build up in this coil, because it's going to affect things like an EMP. So we need to suppress this in normal electronics, because it's basically an EMP, pulse, electromagnetic pulse, And you tend to think of that term in a large scale, you know, oh, this EMP threat that affects, you know, the whole neighborhood or whole city or whatever, like in a big explosion. But this happens on a small scale too. And so I've had to deal with this right from the beginning to prevent, you know, your voltmeters from being ruined. Even your oscilloscope can only handle so much before. I mean, it's built in a way to handle it more, but most devices are not shielded. So they have, like, say, a little capacitor, right? Because it's little, it's only meant to absorb the spike and suppress it as easy as possible, efficiently as possible, for its size, for its cost, whatever. It's never meant to actually enhance the energy, collect more energy. It's not an energy collector, it's an energy suppressor. And I talked about that a lot in the past, I don't need to go into that any further. But, like I said before, if we replace that capacitor with a battery, we're talking about millions and millions of times bigger capacity in a big battery than in a little capacitor. Even in this big, huge capacitor, like when we have the big, I've showed them many times, the big Maxwell 3000 farad caps are still really, really small, like in comparison, not physically, but in capacity, much, much less capacity than in a battery. And that's a common misconception, is that capacitor, that you have the same size of capacitors as the battery, like they're close in capacity. They're not at all. In fact, that big bank of capacitors that I had, the ultra caps, the size of this battery were only the equivalent of like one little tiny flashlight battery in actual energy that can be stored and released. But the advantage of them is that they can rapidly charge and discharge faster than a battery can. So that's their really only advantage. So what we're looking at now is replacing the little cap. That's a suppressor. And we're looking at this. We talked about this in my book with the resonance kit, where we're actually doing the tank circuit and we're circulating the current within the inductor and the capacitor. And the circulating current at the value of the Q factor will be that many times more than the input current with the same voltage. Or if it's a series circuit where the capacitor is in series with the inductor, then the voltage is multiplied according to the Q factor of the parts. So in my kit I provide 100 Q with the coil, and therefore there's 100 times more energy circulating in the one tank circuit, and then we can multiply that out many times. And that's another video. So here we're doing it with the size of the battery. The larger the battery, the more we can collect. And that's not even really in resonance. I mean, in a sense, there's always, there'll be some resonance involved in this, but with the basic systems that we're doing, we're not even showing the full resonance system. So anyway, so now, understanding that, we can move forward. When we put a capacitor across the in and out of the MOSFET, the source and the drain, the S and the D. For those who don't know MOSFETs, they know transistors would be like the collector and the emitter. So we're not talking about the gate here, or the base, the trigger point that turns on the switch, but across the switch itself. So we can think in terms of just a mechanical connection right now, across this terminal and this terminal. So we're going to be doing that over here though, because this is the only way we need the battery charging. That's what we're after. So now, as we put this across here, this is important because as we switch this, there's a diode inside going across here, a reverse diode, goes in the reverse direction. So if the energy's, well, usually it's over on this way, so it's flowing backwards here across the MOSFET. So this is the same effect as right here, right? We're trying to prevent the MOSFET from blowing out. But that reverse diode has a value. So in this particular case, we're using 100 volt MOSFETs. So there's going to be a spike, and we've got the oscilloscope now hooked up to across the MOSFET. Well, actually across the capacitor, which is obviously across the MOSFET. And we're going to see the spike here, and we're going to try and change that capacitor according to what we're doing here, voltage-wise and amperage-wise. So what happens is, this is a very sensitive matter. This is one reason why I kind of avoided this years ago and stayed with the transistors, because they were a lot easier to do the high voltage switching without, they're not as sensitive as these MOSFETs. The MOSFETs can easily be damaged. And this is a very important video for everybody to understand who has one of these systems. This is going to be important information to properly tune your motor to get the most out of it at the basic level. So now, again, as we change the capacitance here, like right now we're going to start with 0.2 microfarads. So 200, let's see, yeah, 0.22 microfarads, or 220 nanofarads. And I've got here 250 volts DC film capacitors. You know, you want them switching fast enough. You know, you can use different capacitors there, but not electrolytic. Fast enough capacitors that can respond to the rate of change. So what happens is, we're going to start off with 0.22. It's going to be the lowest value for this. Because, again, we don't want to exceed 100 volts in the spike across the MOSFET. So you're going to see we're going to get up into about 60 volt spike, and that's going to be good. And as we load down, I'll load down the motor even more than what the Variac loads down. And that way the spike will go up. As we increase the input voltage from the source battery, as we call it, the source battery, the running battery maybe is more accurate, and we increase the load, or the amperage on the system, there's going to be a higher spike across the MOSFET. And we always want to stay, I would say, 90% below that spike, because, or maybe even 80%, because your oscilloscope isn't fast enough to catch the high voltage spike and it only samples out at a certain time. So if you're seeing like 80 volt spikes, then you can count that some of them are going higher than 100 volts, maybe even 150 volts or higher. Now the reverse diode can handle some it can handle a little bit of going over its limit. But what I found is that it's very easy to damage that diode. And once you damage it, it's going to produce a lot more heat. You can run these MOSFETs very cold until you damage that diode or whatever else you're damaging at the same time inside, the junctions of the MOSFET. What happens is it will still operate, but your results are going to be a lot worse because you're creating a lot more resistance across that diode, especially if you're always exceeding the voltage. And you will eventually blow out the diode, or the diode can be blown out altogether, and then it's like an avalanche effect. It's going to ruin the rest. But you can partially damage it. And this is what I've said for a long time. You have to be careful that you don't partially damage. So what we've done for a while is put these caps across that MOSFET in a way that makes the whole motor less efficient, just to be safe. So the bigger the capacitor we put across there, the lower the spike is going to be across the MOSFET, and that is directly proportional to the amount of charge that is going to take place in this battery. So it becomes more of the collector. Just like here now, even though it's not across the inductor, it's still, like Benita said, all you need is one the capacitor just needs to be connected at one terminal across the switch. It doesn't have to be across the switch like you have in your ignition coil. That was a big revelation that I showed a couple of years ago with the Benita system, with the induction coil. Same thing applies here. If you have a capacitance here, or even if you put a capacitance across here, which is also what we're going to talk about in a minute. So this is important. This is going to relate to the next video that I'm going to do on the solar charger, where we're doing the same sort of things. And what happens is, if we have a capacitor, a run capacitor across, kind of like a filter, like you would have in your amplifiers or what have you, inverters, that capacitance is going to affect this capacitance as well. It's very sensitive. So generally we don't need a capacitance across the input battery like we used to do for years when we have the capacitance across the switch. And it's going to be all applied to the transistors as well. So it's not just MOSFET. MOSFET is really a transistor anyway, but anyway, the point is, as we increase the capacitance here, or even across here, then the spike is going to come down across the switch. And we want it to be higher than lower, but we want it to be safe first. Safety first, then efficiency second. So if you want to go up higher, and this is where I can't do much with the parts that we have. If you want to go to higher voltage MOSFET, then you can crank that spike up. And IGBTs are one way of doing that, except the IGBTs are a lot hotter. So you've got to deal with that heat that they produce, which is what I try to avoid. And the MOSFETs and IGBTs are, have become a lot closer over the years. So the MOSFETs are more preferred devices because now they're more rated for higher voltages. So we used the particular MOSFET, and then I guess whenever I show something, people buy out the rest of them. So there's no longer, the MOSFET that we were using is no longer available for another year. So that was the best MOSFET we could find, and now it's gone. And so we had to use another one, which is almost as good. But anyway, the next few orders that people do will get that MOSFET, because I have a few left. But anyway, the MOSFET that we're using has very low resistance, so there's going to be a lot less loss than in typical MOSFETs. I mean, ideally, I'd like to have a higher voltage MOSFET, but it's a trade-off. So what you have is, you might have a higher voltage and you have a better spike, and therefore you can have more charging. But you can also have more resistance, and therefore you're creating a heater, which now you got to deal with that heat. Like here, I don't even need a heat sink on the MOSFET, and running this at 8-10 amps if I have the right capacitor across it. And that's what, again, that's what this video is about, to show you what you want to do. But if I'm drawing more, if the capacitor or the MOSFET has more resistance in it, then you're going to have more losses from the input, because the battery is going to discharge itself at the rate of the load. So that's the trade-off. How fast are you switching? That's another element that we chose in this MOSFET. Very fast switching time. So one of the most important concepts is the rate of change. We're not talking about frequency, that's a different matter. We're talking about the rate that the change takes place from when you turn on the switch. How fast is that? How fast is the gradient? So if you're looking at a square wave, how square is that wave? If it's like this, like a sine wave, that's not what you want, because the rate of change is totally different. So if you have a square wave, boom. And that's what we show in our kit, the resonance kit, where if we don't use the gate driver, which we're using in here, even with the regular oscilloscope or regular frequency generator, we have a lot less output. When we put the square wave on, well, first of all, when we just use the sine wave, when we use the AC wave, you get so much power, but when we use the square wave, we get a lot more, because again, the rate of change is so much better. So then, when we actually have the gate driver, it's a very sharp on-off time. Now, if we go and build one of the capacitors that Tesla was using, which I don't find exist anymore, and we have very fast rate of change, and we could get hundreds of millions of horsepower, he said, out of the capacitors, which is beyond my comprehension of energy. Hundreds of millions of horsepower. But that was all dependent upon the rate of change. So the faster the rate of change, the more energy you're going to get out in all these systems. So we chose the gate driver and a high-speed MOSFET, which gives us the best results. Again, this is all at the basic level. And then of course, the bigger the collector, the more you're going to get out of the system. So those are the factors. Now, like I said, so we're going to operate at 12 volts input, 12 volts output, and we're going to operate around 4 amps running voltage or running amperage, and so that's going to show the lowest power levels. Now, there's a couple more considerations. We're going to go from the low to the high extremes with this motor. We're only going to go up to 24 volts, that's all I've got time for today. And we'll do another video with 36, 48 volts later on. But the same thing will apply, and I'm going to show you how to apply the same thing so that you can do it yourself, 36, 48 volts, before maybe I have the time to give you all those numbers. You can figure that out yourself. But the other factor to consider is, so if you have a battery that's already charged, well, let's go with the other factors first. So the input battery, if it's already low voltage, say you're running at 11 volts, the voltage will be lower than normal operating voltage that we're going to do today. So the spike is going to be lower if you have a discharged battery powering it. And then if the charging battery is already charged up, and it's a small battery, well, it's more in relation to the state of charge of the battery. If the battery's already charged up, that's going to be different than if it's discharged. So we'll look at the discharged battery after, but we're going to look at the input battery being discharged and the charging battery charged. This is going to give us the lowest spike shown. Well, whether the battery's charged or not, you're not going to see the spike so much, but what I'm talking about is the lowest value of the capacitor across the MOSFET here, which I'm finding here, the 2.2 or 22 microfarad capacitor. I'm going to provide these with the kits from now on, a variety of capacitors, so that you can change them accordingly and get better efficiency. Or you can just put the one on there that protects all the different variables here. When we go to 24 volts and we're going to the highest load, then you're going to want the biggest capacitor across there at that point. But if you're going to use that motor at 12 volts again and with little load, then you're going to get less efficiency out of the motor than you could. So I could just provide that one big cap and be done with it like I have, but I'm just showing you this video so that you can squeeze more out of the motors that you already have, if you have the motors already. Some of you are going to try and do that now, make the change. So what happens is, like, you can understand from my perspective, the more variables I tell you about, the more time it takes me to deal with it in customer service. So someone once told me, don't give customers options because it's a customer service nightmare. Because there's always questions, and what about this and what about that, and that takes time. So that's why I'm doing this video, so that you can understand that in depth here. So now, if we're going to look at this running with the lowest settings here, and then what we'll do is we'll load it down, and you'll see the spike go up higher just by loading it harder. And so at that point, there's going to be a point where we don't want to go any further without changing the capacitor. I've already got a capacitor soldered on to change out that one capacitor to a higher value. And that way I can show the whole experiment here. So I guess we could do that. And then, yeah, so the point is we want to keep the spike under the ratings of the voltage of the MOSFET. So it's not just input voltage we're dealing with here, we're dealing with the spike. So 100 volts is the limit of this MOSFET. The bigger MOSFET that I have is 500 volts, and for the bigger motors. But I don't prefer that really because it's got a lot more resistance than this little MOSFET. So anyway, we will go on now to running this, and I will see so 11.9. So we're going to hook it up, and you're going to hear ding, tick, very quiet. And then we're going to look at spike. So I have 1 times probe. So you can see here the spike, it goes negative. There's quite a bit of a ringing. So you can see the ring here. That's the turning off of the coil. And then you see the dip going down. And the oscillation, and that's from the cap there. Oops. And watch, you'll see what happens when we add the extra cap, or the higher rated cap. So what we have peak to peak, about 50, 59, about 60 volts. Now I can adjust this a little bit more, push a little bit harder, and now we're at 60 something. But what I want to do is load it down a bit here. I'm going to take this block here. Whoa! That would not work. What not to do? I should have used a glove of sorts here. Anyway, we can start this over again. I grabbed it. I should have used the soft part. So what I was trying to do, I'm going to bring the voltage down here. Well, it's going to get too high. So now the voltage is climbing. So I'm going to have to use the 10 times probe. You can't really see it without that
So we're at about 65 volts. So let's look at the spike. Well, let me go down a little bit. So looking at that now, so getting caught up here. We're only at 3 amps input. So now 70, 80. So now that we have like 6 amps, which, let me get this a little bit better. Okay, so we're at 4 amps according to the normal running with this load, this 100-watt LED. So now what I'm going to do is load it down. So you can see the, well, I don't think you can see on the camera, but the peak-to-peak voltage now is increasing. So we're already at over 85 amps. So we're only at 6 amps input. So that will be, if I can find something else to load it down more with. That cloth wasn't very good. So if we want to go to about 8 amps, it's burning. Now I've had the generator on. So what I'm doing is simulating what the generator would do. So we're already at 90 plus. So when I go to about 8 amps, I'm already in the 90s. Right? So we don't want to go any higher than that, is what I'm saying. So again, for those who are not familiar, we're charging the battery, we're running these loads. It speeds up under load if we have the right load. We've already talked about that in previous videos. Shorted generator coils. See, there's the terminal shorting. It's not the object of this video, but so in that case, as we were loading it down, the motor speeds up. As we turn off the load, it slows down. So, okay, so that's that. So now we realize that we really need what we really need now is so the 0.22 microfarad caps here, this little one, is good enough for running this with the generator coil as the only load on the motor. Like I said before, the generator coil is the generator coils. When you short them out, the motor speeds up. And so if you simulate the same effect in a load where we're shorting out the generator coils, with the right type of load, the motor will still speed up under that load, like I was turning with the variac. But once we get past a certain point on the variac, the voltage is changing, so forth, then it's not like a shorted, the less shorted condition we have, the less the motor will speed up. And then once we get past that point where it's not changing the motor at all, it will put a drag on the motor like we were doing before, and that will function as the regular generator action. So we move from the EMP, like I said, when they're turn the motor on and off, at both points, turning it on and turning it off, there's a pulse going out in which the generator coils are receiving as receivers. So about 20% of the energy when we turn it up here is received from the motor coils as a transmitting system. But about 80% of the energy will be in the form of regular generator action as the motors, as the magnets are passing the coil, they're creating a charge, so to speak. And that's where you could see the light was still on while the motor was turned off, so forth. So that's not the point of this video, we've already talked about that before, but I just wanted to explain it for those who didn't know. So now what we're going to do is replace the I should always disconnect the input, at least. In the past, I was foolish enough to not disconnect things and blow them out. And when I say past, I mean like a couple days ago. So now what I'm going to do is disconnect this one capacitor. It's a little awkward to reach in here. Because actually I don't want to touch both the positive and negative terminals at the same time. So it's just a little cap. You don't have to have this one. These are just the ones I'm using. They work okay. Probably could get some better, faster caps than these, but whatever. There's no end to improving things. So now I'm going to go with the regular one we've always provided here, which is the, what do you call it? The 1 microfarad cap. Yeah. So 1 microfarad instead of, let me get some solder on this. 1 microfarad instead of 0.22. I think realistically though, at 12 volts, we're looking at, like you're going to see the spike is a lot worse here, or a lot lower. So now, oops. Oops. Too many things unsoldered themselves there, so trying to do this is not very easy on this angle. So before we do that, we'll talk about reactance a little bit, I think, here. Anyway, so now we have 1 microfarad, so the spike is going to be a lot lower. And I should have shown the temperature on the MOSFET. The temperature will stay lower depending on how many times you switch it. The faster you switch it, the more resistance the more frequency there's resistance across the MOSFET, turning on and off. So that's naturally going to have some heat, but since it's so low, it doesn't see it as much. And of course, the more you go over that internal diode's voltage ratings, the more it's going to heat up. So you don't want heat, you want to avoid the heat. So now, like I said, we have these 1 microfarad caps, and we'll be running those in a moment, and we'll look at the spike. Well, might as well just do that real quick, and then we'll go on to turn my meters back on. We time out after a while. All right. See, it's a flat line. Forgot to hook up my oscilloscope. So in this case, I'm going to go back to 1 times probe. I'm going to load down the motor. Load down the generator coils, I mean. Now the problem I have here, I'm going to turn it off for a second. I've got to hook this up, and I don't want to damage it while I'm videoing. Got to somehow connect into the negative terminal here. That's why I didn't want to do it while I was running. It's too hard to reach. And then I'll connect up. So the negative is the source terminal, and the regular probe goes across the drain. So now let's look at this 10 times probe, or oops, we'll change that to 1 times probe. Otherwise you won't see it. Now you can see still about a 50 volt spike, because we're loading it down a little bit harder than we were. So let's look at that again. With a load. this rag here. So notice we're only going not even more than about 60 volts. So I'll tell you, I'm at 8 amps and only about 65. So I want to be able to load this down 8, 9, 10 amps as the maximum at 12 volts. So that shows us the spike. So if we're going to load this down with extra a generator like I showed in the other video, beyond this, again this is really bright, that represents it's hot, ouch. That represents maximum maybe 50 watts. I mean, push it a little bit harder if you have the right capacitance and all that. It's better for charging a battery. If you're going to put a bridge across the output here and then maybe pulse it into a battery, it would be a better use of the energy. And then you could run an inverter, you could run an inverter off of the battery. And that would be fine because the inverter has capacitance in it. So if you pulse it, maybe with an SER, you could do that. Across the battery would be the best thing for this. So anyway, that's what we have for now. Now I can run this at 24 volts. So let's stop it for a minute. Talk a little bit further. So these are 35 amp hour batteries, and we have one little battery here running the Arduino. It has to be isolated because of the spike. The gate driver is the most important sensitive item here that needs to have no real pulsing on it. So we share the grounds with the input negative, and then we have an isolated positive. So you could use a DC converter if you wanted to. So anyway, what I'm going to say is we will go up to, oh, I have them over there, probably the 2.2 farad capacitor, microfarad capacitors, in order to go at 24 volts and load it down at the same time. Oh, what we're going to do also is we're going to run the negative, or the third stage process. But let's talk a little bit more. So going to Wikipedia, electrical reactance, the X, the capital X symbol, is the reactance measured in ohms. It is the imaginary part of impedance. The imaginary part. Isn't that quite interesting? You'll find that term used, phrase imagine, or the word imaginary used frequently. What are they really meaning by that? What's imaginary about it? But anyway, let's go over this a little bit. So this is my old book from the 80s, I think it is. Anyway, going to the sections on inductive reactance. So again, like I said, you got a coil, right? The opposition, wait, let's get the picture out here. So we got this coil here. The opposition to change in current flow that results in the CEMF is called inductive reactance. So again, inductive reactance is the opposition that an inductor coil presents to a change in current. And of course you have all these things in here that are explained, but they're really in the context of constant current. Like that seems to be the idol of the philosophy, the core point that nobody can really free themselves from, that the objective is constant current. And everything is to be understood under the constant current umbrella. You have constant current glasses. Constant current is the most idolatrous philosophy in electronics, in a sense, if you want to compare it to like a religious worldview, or basically a worldview, yeah, that everything comes under that. So like Kirchhoffs Law, as we talked about before, it only relates to a constant current situation, but yet that's the way everybody thinks. Like I've often asked myself, how can people who have studied electronics, especially at the higher levels, and ham radio guys, for example, how can the radio frequency guys who are working with radio frequencies not understand the implications of resonance? And how can guys read these books and see that there is something else which Wikipedia is calling imaginary, and not realize that it can actually do real work? It's a mystery to me. It's like people who can see, who have eyes to see, not recognizing anybody around them. Like acting like they can't see anything. It's just a mystery. Anyway, the point is, the reactance is this change, but it's intricately connected with this phenomena that takes place that can charge up a capacitor or a battery or another inductor, which is what we're going to show in a minute. And then you have, well, let's see if there's anything else interesting I want to read here. When the current stops increasing, the magnetic field stops expanding. And remember that video that I talked about, the MIT professor, Faraday's law, he talks about, was the rule. While the current is changing, increasing or decreasing, the magnetic field is active. And you can have a secondary, which this charging battery is kind of like a secondary, is receiving an output. That's where we put these EMP coils in proximity, because as the magnetic field is changing, it's affecting a change. Well, that's another whole matter. but they're not really getting specific into what other effects are taking place and how to utilize them, because their objective is to have a non-changing environment as much as possible. So they want to minimize that change. So then you also have the capacitive reactance here. So the opposition of a capacitor to current flow is called capacitive reactance, and is indicated by the symbol capital X subscript C. So the other one was capital X subscript L, right? Yeah. So the same kind of things apply to both. The reactance relates to both capacitance and inductance, and the inductor has capacitance in it, you know, and so you have to realize what I want to get at with this is the capacitance is all over the place. Like, don't just think of capacitance in the capacitor. The MOSFET itself has, I think, 3 different areas of capacitance between the 3 terminals, the 3 junctions. There's capacitance, and of course we have to add to some of that to protect it, and that's what we're doing with this video here. But also, the batteries have a sense of capacitance. The wire insulation develops capacitance. The insulation across the gap between the coils has capacitance. Depending on the thickness of the insulation, the between element between the 2 plates of capacitors is the dielectric. So you have to think of the whole environment as different dielectric. So you have within the capacitor a particular dielectric. So you want actually, well, I don't want to get into all that subject, but the air around this whole thing is a dielectric. So between this coil, the motor coil, and like I had before, the EMP coils, those would be like 2 capacitors, and the air between them, the insulation between them, is like a dielectric. So all these things relate to each other. Very sensitive if you know what you're dealing with, if you can have eyes to see that and understand electrostatic effects. They're extremely important with what we're dealing with today here. More so with the high frequency, radio frequency systems, that it becomes extremely important. Like just touching the wire will affect the change, because you become the other plate of the capacitor. So anyway, so what we want to do now is look at what we call the 3rd stage process, and we're going to run this coil I'm going to turn this load off. We're going to run this light so that we don't blow out the MOSFET. It may exceed the ratings of the just gotta make sure I make a good solid connection here. Or wait, I know what I'm doing wrong. Need to do it right down here. Good solid connections. It's not very good. I'm not really comfortable with that because, so what's happening now is what we call the third stage process. Oops. Wrong one. So never mind this battery. Like just have that closed across there. And so now we're adding an inductor right here. And we're going to run, well, this is the option, the bulb. We're just going to run a bridge across here and then the bulb across the bridge. In this case I don't have the capacitor. I should have a capacitor across there as well. And what's going to happen is there's going to be a bigger spike across the MOSFET, which is usually right here. So that's what we have to also do, is protect that MOSFET from the energy flows back into the input. So we have a duplication of the energy going into the charging battery, because again the energy rushes in from the environment, but this resistance here, this impedance, is preventing the charging battery from, like the weakness is in this connection right here to the charging battery. Yeah, coming from here to here. Anyway, we'll talk about it in a minute. Let's just see. Hopefully this is not going to be damaged. Alright, so let's go. So in this case, we are at 10, we need to go to 10 times probe. So yeah, we're exceeding it. Yep. Oops. We don't want that. Ouch. Well, I made a big mistake. Whew. Now I gotta breathe in this. Anyway, so much for that. Apparently, either this wasn't connected properly, or I exceeded the voltage. That was the case in point. So it's going to end our video here. I probably shouldn't have done this because it's not the normal way to run this motor, but I won't delete this because it's important for you to see what can happen. In this case, I'm not sure, because I wasn't looking, whether this light was lighting up or not. I didn't see that it was, so I must have blown it out previously. But anyway, we could see the scope. There was over 160 volts, even though I had the higher value capacitor on there. There was over 160 volts, and I could already tell that this was getting hot. I could smell it. It had exceeded the MOSFET rating. And actually, this was the second MOSFET, so this wasn't the best MOSFET that I have been using. It's a little bit more resistance than this one. I wanted to test it out. Anyway, the point is that you can see how that can easily blow out. So what I was doing again was going from so I should have had the 2.2 microfarad resistor or capacitor across the MOSFET terminals. But so I had these connections here. Really, it was really on this side actually, though. So we placed this right here, and if there wasn't a suitable load, then it blows out. It's too much energy coming back into the MOSFET, unless we have a higher capacitance here. There's nowhere for it to go. So I have to check later on whether that was on or not. If there wasn't any load there at all, then that would explain why it blew out for sure. But otherwise, like I said, you have to have that voltage protected. So that's what I was showing when I showed this video, the first video, selfish circuits, logging path. I was showing this in the box, but I had one of these big coils and 5 smaller ones, and I was driving all those LEDs. So that's what I was doing before. It wasn't anything special. People were speculating as to what it was, but you can see now, I'm giving you an example of a blowout of what can happen. And you can see the board here has a couple of black marks for when things like that have happened. Try not to do that on video, it's embarrassing. But the point is that this is one reason why I didn't reveal exactly what that was, because for the one reason, there's 2 reasons, but one is that you can actually blow out the FET right away like that, and then you know, okay, that's bad. But you can also damage it. Like if I had just gone simply above the voltage rating of MOSFET, which I did, at least I got a chance to look at that and notice that it was over 163. I remember the last number I saw was 163 volts, but it was exceeding that. You know, that was just one of the reading samplings. So the point is, I was way over the voltage rating. So as soon as I go over that for a set period of time at a certain amount, I'm damaging that FET, and then you can't recover from that. And then at that point it will get hot, and it will always stay hot even if you go under the ratings. So that's why I want to say this idea of multiplying the energy out on the output so you can do it on the positive side or the negative side. So really you can see this as a series. This is like Tesla's one wire idea, right? So all relates to that. So I wasn't doing anything in resonance here. Like we've shown that in the past. When we run this idea with the right parts, where we're doing series and parallel tank circuits, like I've shown with the Cron system, where you can see the various diagrams, and the idea of having a whole network here is possible. So if you have everything in resonance, so think about this. At the moment of switch closure, like I said, you're creating this great potential, and the energy rushes in from the environment because it's out of equilibrium. it's broken symmetry, right? So what happens is all the energy rushes in here and on this side too. But on this side, it's more of a closed loop scenario. This is a floating ground here. And I talk about this in the book in a lot more detail in the second chapter of the book. So the idea, this is a second body here. And this becomes a third body. This becomes another body into itself. You know, even though they're connected, you can have this disconnected where we have receiving coils here. So in the book I talk about three different things. The basic system, where you have one floating ground. And then we talk about the one wire output in the second chapter, actually. And then in the third chapter we go wirelessly. So there's three different types of open loop systems. So even though this is still a loop, it's an open loop because the grounds aren't connected, and it's called a floating ground. So this is what we call a multi-body. It's not a single body would be the original configuration. That's a single body. Even though this would be like a second body, it's not used as such. It's clamped out, so it's still really essentially one body. So this becomes a multi-body. And then this idea is the third stage, is what I call it. See, this was expanding the path, so it was like a series impedance that was getting charged up before it could close the loop. So it's kind of like the Newman effect with these miles of wire. You know, the more impedances we affect before the current can flow, the better. So that's the second stage. The third stage is adding another body, a third body, to this network. So this network isn't a single body network. You gotta understand the difference between a single body network and multi-body network. So like I described in the book, the internet represents the two different ideas of a network. So in the electrical sense, the internet is connected in a single body where you have all the electrical components of all the servers and all your computers are all in a closed loop fashion in a single body with a single purpose electrically to transmit signals, so forth. That's a single body network. But the social aspect of the network, of the internet, is the kind of multi-body system that I'm talking about electrically here. So if you imagine the internet as independent bodies contributing to the whole network, that's what is the idea of a multi-body network. Electrically speaking, they're completely independent. They may be affected, they affect each other, as we just saw it blow out. It may be affected by it, but they are independent. They're floating grounds, as we call them. So if you think about it that way, so when we added this extra coil here, because either the load didn't work or the extra energy that was pouring back into the input here blew it out. So it's kind of like running this without being connected. And there may be a possibility that that wasn't making a secure connection there too. I don't know, I'll never be able to tell now. But, so across this path here is, like I said, the negative resistance path. So if I have this in a state of resonance with the motor pulsing, and we can accomplish that by either changing the RPM of the motor and locking it down and tuning it to this system, whatever I have here, and making that in resonance with this coil, or with the frequency of it. Or we can pulse this within the pulses, which we were initially trying to do, but I found it was a lot more stress on the MOSFET to do that, the pulse within a pulse, and I didn't think that people were going to be doing this process for the most part, so we took a step back from that and went with 1 pulse per magnet pass. And then you can see in the off time, oh, I forgot to really draw attention to that, but you can see the waveform oscillating up and down, and so during the off time there is some energy flowing, kind of pumping during the off time. So, but we can create the right frequency. In fact, the motor circuit can go, I've seen about 2.5 gigahertz frequencies off of this little motor at 12 volts within the wave, the pulse wave. So we can actually play around with the different values at the low voltage and low frequency level of the motor, which is nice. We don't have to have, like, to create, you know, the gigahertz switching is a lot more involved, but if we can actually do that here, we can get the effects. So we can run what I call the third stage process, and we can tune it all just right, even with this simple motor, as Tesla talked about that. So that's the thing. If we have this in resonance with the particular frequency that we're tuning to, either, as I said, with the each magnet pass. So if we're at like 5,000 RPM, so you divide that by 60, multiply by 8, whatever the RPM is, we could resonate a load across the charging path, and the battery, once it's in resonance, the battery will not actually see that as a load. The battery will still charge then. Like right now, the battery wasn't charging as much when we put this across because it represented an impedance there, and that limited the exposure of the battery to this negative flow, right? Just so the bigger the materials, the more that it will flow into. That's why the bigger the plates, and remember the plates are at right angles to the heavy side flow. So anyway, the point is, once we make this in resonance, we can add as many resonant coils. That's what I show in the book. As many outputs as we want, as many receivers as we want, and each receiver can then be a transmitter, if we're thinking wirelessly in that case, but we can add them according to the one wire situation. And this is not even adding the ground element to this whole situation. So this, once we add the negative, the ground elements to this whole circuit, we can get a whole lot more energy. So you'll see that this motor in the end is a lot more important than people have underestimated it because they don't understand how the energy works. So that's why I did the book, to open that door, so then you could see how much more you can do with this. So I'm showing bit by bit all these different aspects. Try not to overwhelm people, which I know I've been doing. But for those of you who are ready, you can understand these things and then take it to the next level. So without even doing any of the ground and air ground connections, we can resonate, and this could be the prime mover, and we can have as many times as we repeat the process, we can get more out. Like, you can see how, obviously, if this itself creates the opportunity to charge another battery, then we should be able to multiply that out, right? Which is what I've shown over the years, different ways. But in this case, we don't have to multiply the motor out. It's the mechanical oscillator in which we can multiply this process. I've already shown how we can get more out of using this as a transmitter. We've added the extra battery here, so we get more charge out of there in rotating these two battery banks around. So then this battery doesn't need to be rotated. It can be hooked up, like I show over here, to an inverter. And then of course, like I said, if we add more and more systems across there. So initially when we were showing the black box, we were actually showing a resonant system. For the early meetings 2 and 3 years ago, we were showing the actual resonant box. So you could plug in as many loads to that as you wanted to, as long as we repeat this resonant process internally. And as long as this battery was discharged, that was important too. So we did show that. We didn't show what was inside the box then, and I'm showing you what was inside the basic box. And then the book reveals resonance in the basic form and some advanced aspects too. So yeah, you could take this, I mean, this is kind of as far as I can really show the general public the ideas, and I've given some basic demonstrations here of what you can do. So it's up to you to take that, and if you want, like, you don't really need to go, like this system. Oh, that was the other thing I was going to show. The next video I'll get into the solar charger. We'll get into voltage drops and some practical matters there. What size batteries and how to determine those kinds of calculations. But what I want to get at here is, oh, I need to talk about a couple more things here too in a second. What I wanted to say, oh yeah, I should have had some notes here, but so if this represents, if I put the generator on here, like I've shown previously, like a 50 watt generator, say I have 50 watts of power from, so when I run this at 4 amps, 12 volts, I'm at your 50 watt input from the input battery. And then when I, so that's a 50 watt system right there, right? Like I said, charging a battery is most efficient with that. And then when I load the motor down more, what happens is, like say I have another 50 watts of load on this, this will charge at the rate that this is discharging, you know, more or less, depending on the quality of your battery, the size of your battery and all that. So what happens is, so say I'm at 8 amps now, then I'm at a 100 watt system. So this is what I was trying to do with this newer motor, is create a 100 watt 12 volts, which is reasonable. You know, that's, you know, 12 or 1.2 kilowatt hour a day. Or no, sorry, 12 hour, 2.4 kilowatt hour per day, which is quite a bit, you know, of energy. So if you were then to take that to 48 volts, which we'll do, like I said, I have to get all the capacitor values determined, and I'll make that, there's a slight change in the code. What I said before was, as we adjust the pot here, it'll adjust the on time within the magnet pulse. So what we have to do, once we went up to 36 volts, we found the on time was too long for the code that we have for the 1224 volt. So what we had to do is turn down the pot slightly, otherwise it would go bah, it would run against itself. So we have to change the code a little bit lower to compensate the 3648 volt variation on the pot. So anyway, the point is, it's still the same motor, everything's exactly the same except for the capacitor, and the code changes a little bit for the 3648 volt model. And speaking of that, before I forget, we have now upgraded the Arduino boards to the one with the chip that can be removed. So we're not giving out the code, so you were forced to, if we have a change, to be able to change the code, you would have had to get a new $8 board here, and that's what I pay for them, $8. So, but now we're going to the version that has the chip in there, and we're going to sell the chips for $2 with the code, which we don't make any money off of that. And so with the shipping costs and that, we can change it. So, and the reason for changing it would be if you want to go to the 3648 volt model, which isn't really, you don't really need to change the code for that. All you have to do is turn the pot down, never turn it up to the maximum, and it's the same thing. But if you want to change the battery swapping, like we have with this latching contactor here, which we showed in the previous video, if you want to change that from 1 hour setting, it's an optional, you can activate it with the jumper across pin 5 and 6 there. But it's already in the programming of the kit right now. So if you wanted to change that, like somebody wanted 1.5 hours instead of every hour, then we could just send you the chip if you have the new board. So all the newer orders, all the orders from this point on are going to get this board so that you can change the chip. I'm not a programmer, so I wasn't even really aware that the Arduino had that. We were doing this model, which has no removable chip. So I wanted to say that. So let's go on to what I was just saying, was that you have 48 volts now. We can go maybe about 400 watts. This is what I said before. You know, you're going to really have a lot of power here. So you're going to want to, well, you have to have a suitable load to get that much out of that. So the generator coils are going to produce more output proportionally to the input, which we see at 24 volts. And then, so we go to 48 volts, it's quite a bit more. I wouldn't really make any expectations beyond the 48 because there's a limitation of the voltage here. Of course, higher voltage will always give you better output, but we can't really, when you start to sell things above 50 volts, it's problematic. It's a lot more dangerous too. So, but if you double stack this, then you could have basically 800 watts at 48 volts, which is pretty reasonable. That's really, so really a double stack is all that a small family would need to run their electrical power, not talking about heating, but you know, so that's why I try to make this 400 watts, the single stack, so that it would supply the average electrical energy need for, so the world's average household consumption is 400 watts continuous. So that's what I was trying to do. So 800 gets closer to the North American family usage, which is about 1.1, 1.2 kilowatts average. So we'll talk about that in the next video with the solar charger, those kinds of numbers, and understanding peak loads and all that. This video is long enough, I wasn't going to try and bring it into that discussion into this video, but anyway, so again, this all at the basic level, you know, that 100, 200, 300, 400, 800 watts potential for these motors is all running it just in the basic mode. That is not adding this additional type of output. So you could make this, again, power quite a bit more outputs with that process, but you have to understand resonance, you have to understand this video and what I said about the capacitor. Otherwise, you're going to fail. That's why 3 years ago I didn't show that, because we had to work that out. And you can see how easy it is to blow it out. And once it's blown, like, I won't even touch that board. Everything on that board is not to be trusted again. So even though it may still function if I replace the FET, I can't rely on those parts. So it's an expensive, time-consuming affair to play around with this and not protect it enough. You gotta have secure connections. I should have hardwired all that in there, and I should have started with a bigger cap. So let me just back up a little bit. When we were doing the transistor setup, which is what I was first doing this process on, at 12 volts I was literally getting, under some loads that I was running, like when I multiplied this out with big 5,000 watt transformers, and I had like 5 of them, then, and they weren't in resonance, I was getting 5,000 volts around coming back into the input. Of course, I was blowing out my transistors. So I had various ways of measuring that to do it safely. So the input from that output, that output was creating another input back into the motor, was creating 5,000 volt spikes. And of course, the input battery was charging up, but it was going to damage the transistors. Now, of course, here we're talking about the MOSFETs, and they can't handle that at all. So we have to have that capacitor in there. So it's nice because you can still have this energy surging back into the input, which then speeds the motor up and can make its way back into the input battery, because it's out of phase. It's out of phase with the motor. And the diodes, it goes right through the diodes as if they're not there. So, like when you look at the diagram, why, like, it becomes the one wire phenomena. So if I have it here or here, if I had, which is what I had it right here, how could this battery receive charge from this right over here? There's no way for this pulse, electrically speaking, to influence this battery. So that's, again, getting to the Tesla wire, one wire kind of understanding of things. And that's why I said initially there's a phasing, you have to deal with the right phasing here. And of course, when you're starting to do that, even the oscilloscope
resistor and its capacitance are affecting the tuning. So once you get the basic parameters, then you remove the oscilloscope where you know it's safe, and that's what you lock into. But all that is for more of a constant load that you can understand, and constant input. It's a lot easier than trying to do all this under a changing environment. Like if these batteries are discharging and charging, that's going to change your settings. So all this, so ideally what we were showing 3 years ago in the box and all that was a situation where the batteries weren't changing at all. So the charged battery just remained where it was. The input battery charged up and then held itself. And that was what we were calling the zero voltage, 0 point process, because it was all staying the same. And no matter what, at that point, because we had these resonant coils and systems inside the box, every time we turned one on with its load, we could multiply the energy out again and again. And so that's what we showed in the meetings. And this configuration here is not as, it's not in resonance, so it wasn't going to do quite the same. You can see a slight voltage across these terminals, whereas before we had 0. When we measured it, there was 0 voltage there. And yet, in the front end, you could see the spike. So, like I said, it's a complicated matter, but that is the answer to multiplying the energy out again and again. And that's why the resonance book is so important, because I get into that even without the motor, with or without the motor. The motor makes it nice and easy because it's easy to control this. But like I said, you want to keep it all at a constant. Like I said, if you can tune this so that the coils are in resonance, and like I said, resonance is a relative term. You could be more or less in resonance, but you want to get it so that the input battery just holds. And you want to protect the MOSFET so that it's under its rating, which I went over. And then you keep it all, it keeps itself all together. You have the charging battery discharged so that it's in a state of charge, and then you can run all your loads off of this, and you can turn them on and off at will. So you could have multiple loads click. So say this is running at 800 watts, then I have another module here that I flip the switch, there's another 800 watts output, boom. And then I have another one, there's a second one, there's a third one. And that's not even getting into having a bigger resonant circuit. Like I said, when I was doing the big transformers, it was quite overwhelming, let's just say. And I'm running these things with these little clip lead wires and all this, and it's quite fascinating. So yeah, so I think that's what I wanted to share today. I was going to go up to 24 volts until I blew it out, and I don't have the time to do further, but you get the idea. And what I'll do is finish this out so that with the kits I will provide a variety of we'll put this 1 ohm or 1 microfarad cap on it already, because some people will be fine with that. And then I'll provide the 0.22 if you're only going to run it without a load just with the generator coil load, presuming most people are just going to do that. And then we'll provide a 2.2 for 24 volts loaded. That should provide that, or I may change that, but you're on your own to do this stuff because that all depends on the size of the additive system that you're going to put on there. So it's a long video. I'm going over it from different angles, but essentially it's all summarized in this this capacitor across the MOSFET. I'll have this in the instructions. If you're going to run it 12 volts with the generator coils only as the load, you're going to put the 0.22 microfarad. If you're going to run another load on the shaft, like I was doing, where you're running 8 amps or so, loading down the input, 8 amps or so, then you're going to want to use the one that's already provided, the 1 microfarad. If you're going to go to 24 volts and do that, then it's probably going to be around 2.2. If you're going to use the second one, or if you're going to use 24 volts just with the generator coils, then you could still use that same cap, presumably. Check the voltage, see on the oscilloscope otherwise, but I'll provide the 2.2. So I'll provide 3 caps for now, and then when we do all the numbers in the 48 volt system, 36, 48, we'll have other set of caps for that too. So that's the latest upgrades for today, and we'll see you again with the next video on the new solar charger that is completely unique. No one's ever done anything like this before. I'm really excited about it. Get your pre-orders in for that as soon as possible, because I'm going to limit the first number this next month. First come, first serve. So we'll talk about that next video. I'm not sure when I get that done, but thanks for watching. Hope you enjoyed it.